today, Christian will be talking about something that's very near and dear to my heart, transport and electron optics in a suspended graphene.
Okay. Thank you very much, Jimmy. So it's a pleasure to be here at the University of Maryland. I haven't been here before. Hi. And to talk about that work on graphene, on suspended graphene today. As this is a collaborative effort between the University of Basel and a theory group of Klaus Richter. Here, the two theorists, Ming Hao Liu and Klaus Richter. And the experiment has been done by several students, most notably Peter Rickhaus and this person, Romain Morin, who is now in Grenoble, have started this suspended graphene work. Okay, so I don't want to say much about graphene. So everybody has heard about, know what graphene is, more or less. What they, there's in Europe there's the big, maybe even more hype about graphene because of this graphene. The flagship. This is a big.
Is it really $1 billion, or is that like highly inflated?
It's $1 billion. I'm also a part in this flagship, but there's so many taking part in that flagship that at the end of the day, it's just like for me, one PhD student in this big project. You see. So once the journalist called me and said, "Oh, you are in the flagship. You must be rich." And I said, "Yeah, wonderful, yeah." But there's so many contributing to that. Okay, so we know it's a conductor. It's a good thermal conductor. It's thin. It's optically transparent, and people believe there will be also applications in that area, and that's why European pushed this project. But from a fundamental physics point of view, graphene has a lot to offer, like these features like Klein tiring, Barry phase interaction, strong electron-electron interaction because of low-dimensional system. There is other degrees of freedom, valitronics, etc. And but today I will not really go into these more exotic features of graphene. Most of my talk will just be we'll just talk about simple electron optic effects in clean graphene. So what we're going to discuss, well, we'll discuss with you are experiments that show some features which are due to electron wave propagation in kind of clean suspended graphene, where you can get reflection and diffraction. And to do this, you need very ballistic clean graphene, and so there's a quest for high quality material to do these experiments. Now, when you use graphene in to do transport experiments on graphene, originally people have exfoliated graphene on substrates and made the devices on silicon substrates. And then if you do this on silicon oxide substrate, then mobilities are limited. And so typically, mean free path is not microns, but rather like 100 nanometer or something like this. And it's not easy to get ballistic samples over long distances. So one way to get this now, one way people do get longer mean free paths is using other substrate, like boron nitride is a very well-known substrate now, onto which people put graphene, but also can encapsulate graphene fully, so to also protect it against environmental influences. We decided early on to work on suspended graphene, and that's the topic I'm going to talk about. So I will talk about some interference effect in suspended cavity, like Fabry-Perot type interferences. We will put such devices in magnetic field. I will discuss some other devices, multi-thermal devices, maybe some electron guiding effects. And there are more things you can do, like lensing and filtering, which I will not discuss today. Because picture looks nice, but these devices did not work yet so well. That's why I don't talk about it yet. Okay, how do you make these devices? So we start with a silicon substrate. And onto that substrate, we fabricate metal electrodes, which will be our gates. We're going to use bottom gate structures. And then over this substrate, we put resist, which is called lift-off resist, shown here in green. And then we exfoliate graphene on other substrate and transfer a graphene layer eventually over the gate structures on top of this lift-off resist. And then we fabricate contacts, ohmic contacts, so strain contacts to this graphene layer for electrical measurements later on. And then once all is done, we expose the graphene piece, including some part of the source drain contact by light or E-beam, and develop that area. And then after development, this part is suspended. So we end up with such a structure of suspended graphene. So that's the way we do it. So once it's done, we're going to put this in a cryostat and measure, say, electrical resistance as a function of the gate electrodes. Okay, so that's how it looks like. This is a typical device. So in yellow behind, these are gate lines at the bottom. And maybe the resist layer, maybe 600 nanometer is the distance then from the graphene layer to the bottom. Devices is typically micrometer scale. So this might be 1 to 1 micrometer. It's a bit longer. And you can suspend over quite some distances in principle. We can suspend up to 10 micrometer without having, well, some devices will collapse, but I mean, most of the time it works pretty well. So once we have done this, okay, it doesn't, there's a note, there's still some dirt lying around, so maybe it doesn't look ultra clean, but eventually we want to have really very good material. So now we put this in the cryostat and we measure. And what do we measure first? This is sort of every person doing graphene, they measure the resistance as a function of gate voltage. And with the gate voltage, you essentially dope, or you're drawing carriers into the system, or push out carriers, and then you have the system going from hole doping to electron doping. And in graphene, what is special is that you have this band structure where there is this so-called Dirac point where the carrier density is minimal. When you pass the Fermi level by gating through this minimum, you would expect that the conductance goes through a minimum to a dip, or the resistance goes through a peak. So we gate sweep and you search for a resistance peak. And I can tell you when we fabricate these devices and mount them in cryostat, we find nothing. It typically looks like the green line here, so just nothing as a function of gate voltage, which tells you very dirty material. And what we have to do is afterwards, and it's true, it's really dirty in the beginning. This is all from the resist processing. So there are residues sitting on the surface, which induce some scattering in the material. So what we then do, we do current annealing, current heating in the cryostat, already at the cold. We apply large voltage and drive a strong current, a large current, which heats the graphene sheet. And when you heat this, then stuff is dissolving. And while you start gradually doing this, and each time you have done a little bit more heating, you scan the gate voltage and you go over and over, and all of a sudden peak, or here it's conductance as a function of gate voltage, a dip in this case will appear, and a dip gets more and more pronounced. And if you go too far, you will fill the sample. Okay, that's kind of the risk. So you have somehow, it's always a problem how far you want to go, and there's kind of, you cannot return afterwards. So okay, at the end of the day, what you want to see is a strong dip close to zero gate voltage. If it's really at zero gate voltage, it means there's no residual doping. The Dirac, Fermi level is at zero gate voltage where you would expect it.
No residual doping on the average.
On average, that's correct.
A lot of doping that could be just electrons and holes.
Yeah, okay, there's still a question of how good you puddle landscape,
That's all you know.
Yeah, it's all. Okay, but that's true. Yeah, that's true. The total average doping is going to be close to zero. That's correct. So, but if we analyze this, we can get mobilities up to millions, which are really state of the art, is highest mobilities people have reported on. Now, there's I indicated here. There's there's a fit to a simple model where you take some contact resistance into account and just assume there's a diffusive model with mobility. Then you see there's some asymmetry from the right side. This is the electron doped side. This is the hole doped side. There you get mobilities of something like 800,000 on this side, and here about 700,000, which are really large mobilities.
And why isn't it symmetric?
Well, because there's contact doping from the contacts, and that gives you a different resistance on different sides. So if you go if you dope the graphene layer to N-doped, and your contact would be P-doped, and have P-N junction at the contact, and the other side not. That gives you the asymmetry.
What temperature?
Most of the measurements are done in a 4 Kelvin cryostat at around 1 Kelvin, 1.2 Kelvin. But I also experiment liquid in a helium-3 system, but mostly is, nothing changed much at lower temperature in these systems. So the other way to characterize the quality of the material is one can plot the conductance as a function of carrier density. Now when you go close to this Dirac point, and there is sort of, at some point, the conductance doesn't go down anymore, it saturates at the Dirac point, and the crossover where this saturation takes place is a measure of, measures kind of the minimum carrier density you can achieve on average again in this material. And this number should be as small as possible. That is a measure of a good quality material. And we reach something like 5 × 10⁸. And I noted here some other later work where people achieved on 10⁻11. This is means there's much more stronger puddle landscape, much more carrier in the system. And I think, again, this is kind of state of the art. It's very high quality. It's very good material.
What is the size of your sample?
So,
how many electrons do you have?
So
5 × 10⁸. You have like 5 electrons in your sample? 4?
Well, now you have to count 1 micrometer, 2 times 1 micrometer. So it's
square.
1 micrometer. Now I have to.
So you have like 50 electrons.
Yeah, something like this. Not so many.
And I was going to ask the same thing because the y-axis is like 20s, 30s. So that means that if it's quite ballistic, then that's like.
So that I think this sample here is a relative wide one. Maybe there's something like 4 or 5 micrometer wide. That's why the conductance is larger here. But I mean, no, this one is actually sheet conductance. Well, it goes down to about the value. It should goes down to the right value you want to go.
Okay. Yeah, that is conductance.
Yeah, that is conductance.
So should we worry at all about the fact that your system has actually 5 electrons on the average?
At that here down here? No, I mean.
Well, I'm not doing anything profound. I'm
here,
just multiplying 5 × 10⁸ with 1 micron square.
Yeah, this is around down here, but here you're going to have 10 times more. Yeah, sure. Yeah. I mean, you can ask the question, what's the charging energy involved in all these things, right? That may play.
The that you're quoting, 1 million is where? It's,
no, I mean, okay, you have to worry. This is, in principle, this is not proper to use as a classical model. So I think the mobility, I should say, this number is just using a field effect mobility, but I mean, you can discuss whether that makes any sense. Because if you're at the ballistic limit, there will be also, I will just tell you afterwards, there's still a conductance minimum, and the slope doesn't tell you anything about mobility.
But this mobility that you're quoting, what I'm asking is it at high density? Is it to the extreme right? Or is it near the charge infinity point? That's what I'm asking. When you say fit result, mu is...
No, it's already, I mean, you subtracted the contact resistance already. So if you take this, if you would, then it's a straight line here everywhere.
So it's a constant mobility for,
yes,
the whole red line.
Yes, absolutely. Okay, so the first experiment we'll talk about is Fabry-Perot interferences. Well, just to remind you what Fabry-Perot interference is, in optics, you just take 2 flat pieces of glass which are metallized. They typically have a strong coating such that the transmission is very, very small, so you reflect a lot. And then you get bound constructive interference inside here, with resonances which are pretty narrow. And if you hit such a resonance in frequency, then you get transmission 1, but on a very small, narrow frequency window. And in optics, you can get constructive interference by changing the angles. There's one possibility: you change the width. Typically, in a Fabry-Perot interferometer, one would change d, or you can change the frequency if you wish. So let's see. What we try to do is to realize such an interferometer with using p-n junction as mirror. And here is the device. So there are 3 gate lines now, and 1 middle one and 2 outer ones. And let's assume we gate this in a bipolar way. So let's in the middle say it's n-doped and outside p-doped, let's say. Then you would have p-n junction here and p-n junction here, and you could think there is a cavity inside, and the electron may bounce, maybe partially back and forth, forming standing wave in this system, and we want to see these standing waves in transport experiments when we measure from here to here. Can we see that? And that's the way it looks like. So here's the measurement. This is conductance as a function of the 2 gate voltage. This is the outer gate, and that's the inner gate. Now there are four different areas here. So denoted by the doping. So in the upper right corner here, it's all n-doped, n, so unipolar, so the positive gate voltage is everywhere. Down here, it's everything p-doped. And on this blue part here, you have p-n junctions. So here it's p-n-p, and here it's n-p-n. Now you see where it's blue, you see these lines. These are interference fringes appearing, as we expected it. And we can make a cut here, and you can see there's modulation here. This is a simple Fabry-Perot resonance interference. You can analyze this in terms of wavelengths, and you can count and convince yourself that this is correct. Now, the visibility is very small. It's only 10% modulation and conductance, which tells you, well, maybe not so good mirrors, right? I mean, there's quite some loss, and there's not so much reflectance, which is there. But still, I mean, one can clearly see it. It's very regular. There's no disorder. I mean, these lines are just straight all the way through, so it looks almost perfect.
Now,
So,
how should we think about the nature of the surface of the mirrors relative to, say, the de Broglie wavelength of the electrons? These look like fairly soft mirrors, but what's the de Broglie wavelength relative to the distance over which the effective doping is changing in the material?
it's relatively soft, so it's this comparable. I mean, maybe for the higher order modes, the Broglie wavelength is going to be shorter than the potential, but still, then it's very soft. I mean, the potential changes over a relative long distance, right?
And
It's very soft.
Are the electrons essentially monochromatic in
No.
in this circumstance? And then, if not, yeah, we're polarized.
No, they are. I mean, we apply very small voltages. So the one we are look at, I mean, this differential conductance is in a small voltage window, which essentially you can view this as monochromatic. But you have many different angles. So that's the thing, you average over all different angles.
Sure, but that'd be sort of standard compared to, say, optics, where you might use a monochromatic source, but a broadband source, and then you get the kind of rings that you showed in the previous optics analog.
But in the optic detector, you will be able, with the CCD camera, to view at the rings.
Sure,
so here we just measure just the average over everything.
But on the other hand, if you have a broadband source, so what I'm wondering, what's the bandwidth relative to the de Broglie wavelength? I mean, what's delta lambda over lambda for the effective ballistic electrons?
I mean, the source is, I would say, is very monochromatic on its on the energy scale. I mean, the delta lambda, which is coming from the source, is very. I mean, the delta omega is very small, I would say.
But how small relative to?
I mean, I would have put in numbers where I don't have numbers with me at the moment.
What bias did you put on, like a microvolt, 10 microvolt?
I mean, I think it's rather 10 microvolt.
Yeah, so it's like 1%.
Yeah.
And what's the order of the like how many half wavelengths of the de Broglie wavelength are between the mirrors?
Oh no, it starts essentially. You see, this is the Dirac point. The wavelength is infinite here, so it starts. This is the first one. The second, just
okay,
the,
so
it
goes
just start.
From order 1 to order maybe 10 or something.
Yeah. You start. It's not a long cavity. It's compared to wavelengths. It's really long. You start at the smallest carrier density with the longest wavelengths, and then wavelengths get shorter. Okay, so now the visibility is small, and we would like to understand why the visibility is small. And so when one has to, one has to understand the transmission probability through such a p-n junction. And to do this, just look at one p-n junction. And so this is now a different device, which has just the gate on the left and the gate on the right. So it says in the middle one junction. And so you can try to measure transmission probability and reflectance probability in these systems, in this device. And when you view this in a sort of quasi-classical picture, then if you would come in with trajectories, with waves at different angle to such a junction where the carrier density goes to 0, meaning the wavelength goes to infinity, then actually you would diffract away from this region, getting closer to the surface, you will just diffract away. And if you get steeper or more normal, you get closer to this interface, and on the opposite side is a mirror trajectory. So you can think that you would have to tunnel from this point to the other side. But if you come normal, then the tunneling distance gets very short, and then transmission is expected to be large. And it turns actually out that at normal incidence, you cannot reflect, just because if you would reflect the normal incident, it would flip. There's another degree of freedom in graphene. It's called the pseudospin. You would have to flip this pseudospin, and that's then not allowed. And therefore, at zero incidence, transmission is 1. This is called Klein tunneling. And it means that if transmission is 1 at zero incidence, there's no standing wave pattern can form, and that's one reason why this visibility is small. But on the small angles, there is some partial reflection still, but you also have to see at larger angle, nothing will go through, and nothing will contribute to the current. So what we see in the current are only the things which really transmit, and they are only appearing at small angles, and at small angle transmission is large. And that's why visibility is small. Now, this is what people have calculated for such a p-n junction transmission probability. It's this tunnel, it's kind of a tunnel exponent term, and it has this angle dependence, the wave vector, and when this is kind of measuring the smoothness of this, this is calculated for a smooth potential variation, and D is kind of the length of this potential variation. Now, you can use this formula, you can just take this formula and put this also in Landau-Büttiker equation and just calculate the conductance you would expect just by summing over all the modes. If you have now if the certain has a certain width, there's a number of modes, you sum this up, convert this in an integral, put this in, calculate it, turns out it becomes square root dependent on the wave vector. And now you can just plot it. And this is what you theoretically would expect, this square root function. And that's where we measure the red part. And you see now in the measurement, now coming back to this field effect mobility, somebody asked.
That's KF over D, that should be dimensionless.
This is conductance per width.
This is conductivity.
This is conductance per width.
Ah.
This is conductance per width.
There's the length here.
Yes. Okay. So I'm asking. Yesterday in the hotel, I looked at the same thing, same question. Said, what's going on here? So now this is ballistic calculation. Perfect, ballistic. And it also has a slope. I mean, you cannot take this slope and say, I'll calculate the field effect mobility. You would get a finite mobility, although it's perfectly ballistic. So now you see in the experiment, it has almost the same slope, like in a ballistic case. It's a little bit shifted because there seems to be some additional doping in the system. And you see some additional modulation up here. I'll come back to that. But the slopes here are almost comparable. This gives us kind of good confidence that our system is quite clean. Now why do we see additional modulation? This is now a p-n junction. And in an ideal p-n junction, there's no cavity in this sense. But the reason is just because there's also reflection at the outer contacts. And again, you have cavities left and cavity right. Because because of contact doping, there will be a potential step there, or even a p-n junction at the contact, which gives partial reflection. And then you get standing waves here and standing waves here, and you get additional interferences. And again, I show you a plot.
I have a question. So you're not seeing any disorder effect like Philip Kim saw because your samples are so clean, right?
We don't see any disorder effect here. It's very clean.
Ultra clean.
Yeah,
That's the new development.
Yes.
I have been out of it for 5
Yeah.
years. Right?
Yeah. It's just like, okay, it's hard to find anything which has to do with disorder. I mean, it looks pretty clean. Also, if you compare with calculation. Now, this is a p-n junction now, and again, these are it has 2 gates. This is now right and left gate, and well, sorry for the right and left. Okay, so maybe the other way around. So this is left now. Okay, so again, you can see these lines here, interference lines. There are also lines actually here, and they correspond to different cavity interferences. Okay, I can just indicate them here. These lines in this direction, parallel to this Dirac point, are just standing waves in here. These lines in this direction, standing waves in here, and in unipolar you also see some of them. Okay, so putting all together, again here's visibility is very small, but the reason why visibility is small is just because what we see, most of the current we see is the one which is transported parallel, which is at small angle, and at small angle transmission is large due to Klein tunneling. That's in a nutshell the explanation of what we see. Now we asked our colleagues from the theory group to calculate this, put this in a time-binding model, and gave them the geometry of our device, and it's just what they calculated. This for this device, which I show here on the left. And you can see there's one parameter in the theory, just one, which is the contact doping, which we have to put in. And you see that it looks, it looks very much similar, has a bit more visibility. Maybe this is because maybe the contact doping is not exactly the same as what we have. But from, from this order, so you don't see, there's everything regular in the experiment as it is here in the theory. There's another one, this is from an earlier paper which we published. You see this is a similar p-n junction. What we plot here is, we differentiated the data that you can see the lines better. And this is a measurement here, and this is a calculation. So it compares really, also some of the really detailed features compare very well. Okay, this is Ming Hao Liu. Okay, so now this was the warm-up. So now we want to put this in we place this stuff in magnetic field. And in magnetic field, when you have a p-n junction, you can have guiding along the p-n junction. And I would like to discuss this here. So when we had a sample, this was Christmas 2 years ago or so, where my student was measuring between Christmas and New Year. And it was so beautiful that he couldn't stop because this was the sample he had. But fortunately, the sample died then, and he could go home. And so that's a p-n junction as one gate voltage, and which goes from the bipolar regime, so it's p-n really doped, to the unipolar regime as a function of magnetic field in this direction. And you can see it's very small field scale. It's only below 1 Tesla, and you can see a lot of stuff. It's full of features, and it has features down here. It has a lot of detail fanning out here. It has states that disperse downwards in magnetic field, some that it's dispersing upwards in magnetic field, some that don't disperse at all. And so the question, what are they all? So we always try to reproduce, get another sample of this kind. Never got such a sample of this kind anymore. So can still try to get, we still have beautiful, perfect samples.
What do you suspect was special about this sample? Homogeneity? All your samples are homogeneous.
No, there still we have samples like where we see part of these features at similar quality, but not all of them, at this quality, at that level. But most of this, we don't understand everything still yet. Some of these non-dispersing features we still don't understand, but all the others, most of it we understand in the meantime. Well, I will try to explain you some of them. So if you go at zero magnetic field, then the lines, the interference pattern you see is just the Fabry-Perot interference pattern. If you go slightly out in magnetic field, then you just distort, because there's now a Lorentz force, so the trajectories are bent a little bit. And if the bending is very little, you still have Fabry-Perot interferences, which are modified, because there's now flux, an additional phase term in the system, and that gives this some dispersing features. Now, if you go a much larger field, so that the cycloid orbit fits into the sample size, this is when this blob ends. This is outside here. Okay, so that gives this shape of this feature here. So now there are 4 different regimes you can think of. The small field regime, which people have looked into it. There is something where you can have bound states, special bound states appearing in this cavity. And then at larger magnetic field, smaller cyclotron radius, you can get skipping orbits along the edges, and then they skip along the p-n junction, and they're called snake states. And at larger field, everything gets, wave function description, quantum Hall regime. So now this one is pretty well understood, and also this one is pretty well understood. So I just show you quickly, but there's not much to discuss now. This is the sample I showed before, and we just put it in magnetic field. Still very small field. It's only not a Tesla, 200 millitesla. All the interference fringes are gone, and then you see quantum Hall plateaus in this plot, right? So very nice, and this plateau should be at 4e²/h, which is very nice, which is there. Also on this side, and then you see the typical filling sequence of monolayer graphene. And here you see a lower conductor. Here you have a p-n junction, and the conductance is lower. because now these states along this edge is split into parts going to the left and parts going to the right. Okay, so I want to talk about the snake state next, and that's actually we follow up. There has been done work here before from Jimmy, but that was done in I think supported devices a bit smaller, where they found evidence for snake states already. So what we were looking for, I would try to explain is like this. We look for feature which has to do with this trajectory, which is following along this edge, where because of the p-n junction, because of the opposite, because you are, can say the opposite mass, or maybe not so good to say so, because you're on the below, in the valence band, you rotate in the other direction for the same field than when you are in the conduction band, you get this cyclotron motion along the edge. Now, assume that you would start at the lower bottom at a fixed point. Let's assume that this is the case. Then when you follow this trajectory in a quasi-classical way, and you would at the end up on the left side, then you would skip back to the left part. If you came from here, if this was your source contact, you will end back to the source contact, which means the reflection probability is kind of increased. If, on the other hand, the cyclotron orbit here is now the radius is smaller, slightly larger field, you would end on the other side, on the right side, you would skip to the right side, and the transmission would be enhanced a little bit. So you expect in this picture that the transmission probability somehow will oscillate, something with magnetic field, but something which is sort of following the width. So if the multiple of cyclotron orbits, in the width, this will follow commensurable with some commensurability criterion, which includes the width. Now, if you look at the cyclotron radius, how it follows, the cyclotron radius is given by momentum divided by magnetic field. And in monolayer graphene, graphene momentum is proportional to square root density. Now, if this radius, say, is 1/5 of the width, or something like this, right? Then we look at this being a constant. Then you will see that the density will be quadratic, will be proportional to magnetic field squared. So this pattern of periodic modulation will follow parabolic lines. So I've just drawn some of these parabolas. So the yellow one, where the width is 4 times the radius, next one 6 times the radius, and so on. So let's see whether we can see some feature in the data which has this parabolic shape. And I explain it because it's there. So here's some data. So this is a gate voltage in a p-n junction in magnetic field. As a function of magnetic field, where the gating is in the bipolar direction. We gate like this, right? It's always p-n, but just always opposite densities on the two sides. And now, if you go into increase the magnetic field, then down here the cyclotron radius is still far larger than the width. But once you cross out here, then you get the width becoming larger than the cyclotron diameter, and you start to get this. You get this cyclotron motion along the p-n junction, and you can see these lines here appearing. And if you differentiate this data, that you can see better, then you see this here. So you can see something which, it's not really like parabolas, but something like a parabola. You see these lines appearing here. And now the question is, are these lines is this explanation correct? So now again, we asked the theorist, could you calculate this? And they could. It took a little bit longer because the magnetic field's probably a bit harder to do. But this is the theory of this experiment. And they did the same thing. So this is the conductance, and this is differentiated data. And you can see these lines. And there are different sets of lines. And we see also them in the experiment. There are other sets up here, which also are appearing, as you can see them here, fanning out. And now we ask the theorist also, well, are you now sure that this is due to, the the snake state at the p-n junction? And the nice thing about the theory is that they have the wave functions. We just measure the conductance, but now you can look at the wave function. So that's what they did. So we will make a cross-section in this direction and look at the wave function. So that's plotted here is essentially the current density in x direction taken from the wave function. And you can see here's the p-n junction. And x direction is horizontal. And I mean, okay, there's something messy here. So that should be the snake state here. And now you can see it changes the color, means changing sign. So this positive, this is negative current, positive current, negative current. So you know, it looks like this is snaking around here. Okay? So now you can also look this in a movie. So what we look at is we just follow one of these lines, one of these conditions, where you see maximum here in conductance, maximum in transmission, and you can see that exactly on this pattern, this snake state is stationary. So it's really true that this is fixed, right? It doesn't change as you expect. While if you go across these lines, then this one is moving because now you change the number of cyclotron orbits in the width. And this gives rise to this modulation in conductance. Okay, so that's kind of the interpretation. So the pattern we see, these lines we have been seeing, are due to this formation of the snake states, and they somehow give rise to modulation in transmission by this commensurability criterion. Yeah.
So does the width of the junction come in critically to the story?
The width now in the x direction, in how smooth the potential is.
As you go through the p junction.
Well, whether it comes in critical, I don't know, because we're not changing. We cannot change this very much. I mean, because we are just this distance away. We are like 600 nanometer away. We never change these parameters so much. I wouldn't expect. Well, no, I don't think it will change so much. But I mean, we didn't play around with this parameter in really large scale.
Did the shape of the edge matter?
I mean, this edge here.
Yeah.
Well, is a good question, but I don't think very much because the magnetic field is skipping. It's skipping anyway in the right direction. But I mean, what disorder the edge? This is another question. What in general will disorder in our experiment somehow on the edge matter? As long as I would say my answer is as long for large wavelengths you average kind of over atomic disorder would be my expectation.
Specular reflection, right? That's what you drew there. I mean, they have to assume something.
Yes. That's
Specular. And so perhaps that's the important thing. Perhaps this comparison is showing that experiment you have specular reflection, and that's not obvious to me.
Okay, well, in the theory, we just put in, essentially a perfect edge. But recently we started to change this edge to some steppy edge.
Right,
and now there are interesting effects appearing, which you also see in the data, so kind of new effect, which are, the next order of effects we start to see in the data.
But focusing with the edge graphene, so you know that predominantly it's specular.
Right. I mean, this is, to me, it's very revealing.
Yeah. But the main features we see are specular and mostly due to the fact also we average over these long wavelengths. Yeah.
Well, but is there a canonical perfect edge? I mean, it's a hexagonal lattice that you're cutting, and that to at an angle, so it's not armchair or zigzag or something.
No. So we have calculation where we just did parallel, but then we also asked our colleagues to do sort of real experimental samples, right, which have any angle. And then you have to model this in this way, but then what he was doing, it was just going from zigzag to armchair to zigzag to armchair, zigzag to armchair, like this, in a regular way. Yeah.
Probably for theory, the only thing that matters is specular or totally diffuse. That totally diffuse a theory cannot really say anything because then it becomes very complicated. But it is specular because look at the agreement.
Well, the numerics. I mean,
you can't argue with the agreement.
But is the graphene structure significant compared to the inverse K vector here? I mean, it seems like.
No, I don't think really. Yeah.
Yeah. So on that scale, it's going to look smooth, right?
No. So we actually use this also. We scale. I mean, to do this calculation, we scale the graphene up. Essentially, the feature of the graphene essentially doesn't really matter much on that scale.
Are the cyclotron orbits is essentially classical, that is high angular momentum states?
I mean, there's a transition from classical to quantum at this place. I would think for this regime, you can think of classical. Yeah.
But the theory is completely quantum mechanics.
It's,
that's what you told us.
yeah, the theory is completely
Klaus
quantum.
actually calculates the
Absolutely.
full, I mean, I know him.
Absolutely.
He does the full thing.
It's the full thing. Yeah, it's the full thing. But it's nice that it's still the picture works wonderful. Okay, so I jumped here. So, well, this is a way you could use this guiding as a kind of a switch. It's maybe not an effective switch, but meaning you can use it to guide you guide electrons from one side to the other, and it has some similarity. Maybe that's also interesting to edge state at a superconducting two-deck junction, because there when you come with an edge state here to a superconductor, then you will convert electrons into holes and holes into electrons, and essentially you can view the part on the other side as sort of the whole part, and an edge state at a superconductor would somehow behave similar than such a snake states at a p-n junction. Okay, so now I have to ask. So how long should I talk, or can I talk? Am I allowed to talk?
10 or 15 minutes.
Huh?
15 minutes is the allowed.
Is the allowed?
Yeah.
Okay. So do you mind? I just skip a few things, right? I mean, I will not talk. I mean, I just show you a quick picture here. So we also do. We do more complicated devices. This was a test whether we can make a mirror, a beam splitter, where the gate is now inclined under 45 degrees. And we have 4 contacts here, like contact here, and also these 2 here, so that you can really have like a true optical beam splitter. And these devices are fabricated now on a much larger scale. So usually we fabricate many of these gate structures, whole arrays, and put the graphenes on it, and then we suspend some of them. And so in the cryostat, you typically have many samples, and this is needed because this current annealing step, usually, sometimes you just kill your sample. There's a certain destruction taking place, but you always want to have afterwards at least 1 or 2 great samples to work with. And actually by this method, if you make an array or a couple of them, the yield essentially is always 1. So we always have something to work on to measure later. So, okay, so I will not discuss this because for time reason, but I will just jump to that one here. So question, can we also guide electrons using electric fields? And also there's work from you before, but that's, I think we do everything just a bit more cleaner than what you have been doing before. So we try to guide electrons by electrical potentials now. And since an electric potential well, you can confine the electrons to some degree. And let's see whether this is possible. So the way this is done is that we have now contacts also at the edge, like 2 additional contacts, which are lying above a gate line underneath here. So, okay, so here's a sample, how it looks like. I also must say that samples you see, they've never been measured typically, because the ones we have the great results on usually end at death. So, we just play as long, at the end we heat a little bit more, say, no, more mobility or cleaner, and until the sample, when we take it out, it's no longer alive.
So what's the death mechanism? What happens to it?
Just probably gets too hot, and then, and then rupture. You can see already here there's some strain in it, and here there's a critical point, it may rupture. If at some point, yeah. Okay, so we first, again, this sample we will current anneal and measure source strain from here to here, and it's much harder to get this sample clean. And the reason why this is very hard here, if you have more than 2 contacts, then what you actually do with current annealing, you heat the graphene sample kind of mostly in the middle. And at the contact, there's still a heat sink. It's cooling. The contact is, and if you have middle contact, which you don't heat, this one will also cool. And therefore, you somehow have a problem now that you want to heat over all the contacts, but you only have 2 contacts. So what we do, we heat from here to here, then we heat from that to that, and so on. So we repeat this multiple times in the hope that we get all the dirt dissolved. But not all the dirt dissolves. I can tell you some of the dirt is also then collected, the cold parts. And then you just push around some of the dirt when you heat from the other place. And so you never get everything completely away. Anyway, so here is the measurement. And again, seeing these interference lines gives us confidence that it's quite clean. So now what would you expect if you measure from here to here? Can we get, why can we get confinement? So if you have a p-n junction, we know that we can get some confinement. So all trajectories classically which come on a large angle will be reflected. And there's some loss for trajectories which are almost normal. By Klein tunneling, they will loss out into the outer part. So we expect some collimation or some collection through this channel in this region where you have p-n junction. I indicated already where these regions are. Based on these zero density lines here, you expect it somewhere here. But now there's another process which you usually use in normal fiber optics. In fiber optics, you don't have p-n junction. P-n junction would mean negative refractive index. Okay, you go from electrons to holes. But you have just one, just have a refractive index positive here. But if you go from high refractive index in the core to the low refractive index outside, you can have total internal reflection if you're again, coming in not too steep. And the same can happen here. We can also have total internal reflection in principle, and that regions are indicated here with the other color. This is the regions where refractive index would be larger inside than outside. So now here's the experiment. So I should tell you what we do in the experiment. We apply a bias here on the top contact, and then a current is injected into this region, and we measure the current on all the 4 leads. And now we compare the current that comes here. This is the one we want. We want to have more current here, or a lot of current here. Compare it with the total current we inject. Let's say there's also current appearing on the other contacts, kind of the loss. So what is plotted here is the conductance from top to bottom divided by the total conductance. And you can see, as expected, where I indicate where these 2 regions overlap, there's the largest transmission from top to bottom. This is the red part here. So I overlay this here, so that's fine. So it's kind of what we expect. So there is an enhancement. I mean, it's not super large. I mean, you can still see there's a lot of loss. So we get maybe 40% at maximum down to the bottom. Now, if you come from this region here, from the unipolar side, you would expect that it starts to collect, essentially passing that border. But you see, initially it actually dips downwards. It's even anti-collect. And then only at some point, delayed here, there is some additional increase in conductance. And now if you go along this direction, you see that there is something like steps, right? And I indicated here. So now I make some cross-section in this direction, a couple of them. These are shown here, and you can see there's steps, right? Kind of steps. I mean, at least the first one can clearly see as a step. And so what are these features now? And this is just the fact that this wavelength is large, and it has to fit into this wire, and then only then you can have a bound state in the system. So if it starts at very low carrier density, very large wavelengths, it's not possible to have a bound state along there. So now we also calculate, this was also calculated, and you can see the same features here. So it's the large collection here, and if you come from this side, you see first at E, there's also, you can look at the wave function, you see actually it's almost an anti, I mean, there's no occupation, it's the opposite here, there's no probability of electrons here, everything is outside. But all of a sudden at position D, there's one mode trapped. So the first mode in the channel is appearing at this position. That's where we see the step. And then, okay, there will be multiple steps maybe. You could maybe resolve. But there are other features here, these other lines. And these other lines are Fabry-Perot interferences because also the outer system, the cavity outside with the contact, there are standing wave patterns appearing, and they interfere with the rest. So now we can look at cross-section and compare. And essentially what you would expect in a perfect wire, you would have quantized conductance, okay? But this is way away from a perfect wire. We get a little bit, we can get electrons confined in the system, there is some loss, and in a perfect Y there would be quantized conductance of 2e squared over h. Here, the mode, there are 4 channels, would be 4e squared over h. And in the calculation, you can see these steps here. They're very weak here. This is the first step here, 4e squared over h. That's the next one here, up here. It's a little bit because there's contact resistance taken into account as well. And these other lines, which are not constant, these are interference pattern. So that makes this thing a bit confusing. But in the experiment, you see the same thing. You see horizontal steps. Weak here, so you see one. And you see the other lines here. Again, comparing very well to theory. Okay, so there is only a collection. Well, we can say what we see there, we can guide the electrons in electrostatic potential. We can see mode formation. So you can see the quantum nature of these waves in this channel. There's still quite some loss. And the loss is not surprising because if you look at this picture, we assume you apply a voltage here and you check from this side or also on this side, you can have a lot of current just going perpendicular out here to the other side. And it's just like, you know, it's just passing the p-n junction because it's perpendicular to the p-n junction. Now we try to improve this by making these devices, but they have so much strain here, they rupture quite often. So they're we have not been so successful with those, actually. So here is what I've been talking about. I have skipped this. I didn't talk much about this. There are other things we are working on, like superconducting contacts and ferromagnetic contacts for spin injection, and maybe also we're also working on CVD graphene. There's a grown graphene. I didn't tell you the graphene we were using were exfoliated graphene from crystals, but today there's big effort to making the CVD graphene crystals more perfect, better and better. And it's also, I'll just show you this. This is an interesting development. These graphene flakes, typically the exfoliated ones are small, like micron, a couple of micron. But in CVD, they have been growing and become single crystals. So there's almost sixfold. Then you can see the shape here. This is a single crystal. If you put it on a TEM grid and check it, it's everywhere the same orientation. And now these things can be grown even larger to centimeter scale today. And I just show you a picture here. This is what you look at. This is a copper foil. And on copper foil, we grown single crystals of graphene, and they're hexagon shape. And you don't need to see through the microscope, so you see by your eyes. The hexagon here is the graphene. Now you say, why do you see the graphene? It's a monolayer. It's just a trick here. It still lies on the copper surface, and after growth, you don't see anything. But then we just let it in air, or we put it on a hot plate, and then the copper oxidizes around the graphene and changes color. And afterwards, but you can see it by your bare eyes. Okay, so that brings me. With this, you can make much larger structures. These are all suspended, very large. And I'll just skip all this stuff here. Let's see, an end here. Oh. Okay, so I haven't done the work. Yeah, all the other guys here did the work. It's really has been fantastic to work with all of them, and it's been great to come here. And thank you very much for your attention. And I'm happy to receive more questions.
The electron optics part, which is so nice, what is not clear that what specific aspect of that connects with graphene? If you have some other